Well, I'm very pleased to introduce the speaker, Adrian Escobar. I guess most of us know him as a member of the audience at real seminars, at in-person seminars in Montreal. Adrian was a postdoc here, a laboratory postdoc associated mainly with Michel Grundland and myself. He was here for 3 years, then he left for Mexico, and now he's got a tenure track position at UAM, not to be confused with UNAM. The M in UNAM stands for Mexico. The M in UAM stands for Universidad Autonoma Metropolitana. They're both in Mexico City. And well, I think I would like to congratulate Adrian on landing this virtually permanent position. And we'll invite him to start talking on the title that is announced.
Thank you, Pavel. Merci à tous. Je suis très content de participer encore dans le séminaire de physique mathématique. And as Pavel just said, I will tell you about some progress on this subject of superintegrable system. This is a work done in collaboration with Pavel and a collaborator here in Mexico City, Roman Linares. So this is my plan for the talk. I will start with the introduction, so the basic definitions, the systems I will be considering, and then in section 2, the formalisms of higher order superintegrable system will be presented in a very short way. In particular, the general n-order integral of motion, and the last 2 sections will be about some what we call doubly exotic and doubly standard potentials. It will focus mainly on the quantum system, but of course I'll mention some few results on the classical case. So, okay, let me start. The system I will deal with is very simple. I have a particle on the plane, so it's a spinless particle on the Euclidean space E2. The classical Hamiltonian is presented here. As usual, we have the kinetic term plus the potential. I'm using Cartesian coordinates, so the scalar potential is an arbitrary function of x and y, and px and py correspond to the canonical momentum. So the picture is as follows. We have a plane. In the plane, there is a particle with unitary mass, and the evolution, the time evolution, the dynamics of the system will be governed by the scalar potential, which so far is arbitrary. What we want to do, well, so this is the formulation of the general mathematical problem. Let's try to find all potentials for which there exists 2 extra integrals of motion. So in addition to the Hamiltonian, we are looking for 2 extra quantities, but the special thing is that they have to be polynomial in the momentum variables. So here I present a capital I1, so it's a polynomial in Px and Py of order m, and I2, it's the same, it's another integral of motion, so it means that both functions Poisson commute with the Hamiltonian, but they do not Poisson commute among themselves. If we can indicate and write such 2 extra integrals of motion, in this case we call the system maximally superintegral. Why to study such, before that, the quantum version, it's of course very straightforward. The Poisson bracket will replace by Lie commutator, the Lie bracket, and the originally functions defined on the phase space, they become nothing but operators under the standard quantization procedure. And the conditions to have a superintegrable system are written at the bottom. So they commute with the Hamiltonian, but not among themselves. So what's the main motivation to consider such system? Well, in classical mechanics, we know that all bounded trajectories have this remarkable property that they are closed and periodic. This is a theorem. And moreover, in principle, we can find these trajectories without using any calculus. In quantum mechanics, the situation is more or less similar, more or less because, as we know, There is no an analog of Bertrand theorem for quantum in quantum mechanics, but actually a conjecture born in Montreal in 2001 is that all maximally superintegrable quantum systems are exactly solvable. It means that the spectrum and as well as the eigenfunction can be calculated by pure algebraic procedure. Let me start and give the main properties of second-order superintegrable systems. So it means that in addition to the Hamiltonian, the two integrals have of order 2 in momentum variables. From the very beginning, it was found the remarkable connection between second-order symmetries and separation of variables. And in the last two talks in the seminar, we heard about this beautiful, profound relation between such systems and the theory of a special function. And moreover, there is, I should emphasize, the very rich structure of the polynomial algebra generated by the integrals of motion. Another important feature is that for second-order superintegrable system, the potentials in classical and quantum cases, they are the same, they coincide, and they satisfy a linear partial differential equation. To summarize the results for this second-order superintegrable system, here there is a table. So there exists 4 families of superintegrable systems, V1, V2, V3, and V4. Each of them depends on 3 parameters, alpha, beta, and gamma. And as we can see, they can be considered as a isospectral deformation either of the harmonic oscillator or the Kepler problem. The next is to ask, what about higher order superintegrable systems still on the plane, but with integrals of order larger than 2?
Could I just ask Adrian a very quick question?
Yes, please.
Why are you requiring your integrals to be quadratic in momenta?
Because this is the simplest case. So we consider m and n equals to 2. Since the Hamiltonian is already of second order, this is the first systems to consider.
So it's just an ansatz. There's no special reason for it.
No, well, but they have this special property that it leads to separation of variables.
Okay.
Yeah. So this is all about second order. And if we ask about on higher order integrals, let's keep one of them equals to 2 still. So we maintain this separation of variables and let the other be larger than 2. In this case, exotic potentials arise. What they are? Well, exotic potential, by definition, we will see that they do not satisfy any linear partial differential equation, but only nonlinear ones. In the quantum case, the equations for the potentials, they will pass the Pauli-Bettel, so it's a conjecture. And more importantly, now, if one of the integrals is of order larger than 2, classical and quantum potentials, they can differ. This is another difference with second order superintegrable system. So let me start with an infinite family of higher order superintegrable system. In 2009, the two-dimensional n-order superintegrable system TTW was introduced. The potential is presented here. It depends on 3 parameters, alpha, beta, and gamma, and r and theta are nothing but the standard polar coordinates on the plane. This potential admits a higher order integral of order n, and is given in terms of this small m and n, which themselves fix this parameter k. This potential unifies very well and celebrated examples. For example, in particular, at k equals to 1, we recover Smolodinsky-Vintorn systems. K equals to 2 corresponds to rational VC2 model. And for k equals to 3, we again have Wolf and Colangelo model. And it had a very great impact on the field of superintegrable system. So it unifies a lot of them and presents an infinite family labeled by this integer n. So in 2018, with Pavel, we studied in detail this kind of system that admits separation in polar coordinates. So they have this generic form. It turns out that for the radial part, we only have basically the harmonic oscillator, and the non-trivial part is encoded in the angular dynamics. What we found is that the TTW actually is one of the 4 big classes of potentials that appears in the case of separation of variables in polar coordinates. More specifically, it's a standard potential because it satisfies a linear ODE, and it classical in the sense that it does not depend on H bar. But also, already at the classical level, exotic potentials arise. It means that the angular part now is not given by the solution of a linear ordinary differential equation, but a nonlinear one. We check that such equation does not pass the Pain-Levé test. And then we move to the quantum case. In the quantum case, in addition to TTW, there are pure quantum potentials, so they depend on H bar in such a way that in the limit H bar to 0, we don't recover the TTW. So it's a new potential. And more interestingly, there are quantum exotic potentials. In that case, the angular dynamics, well, this function T, obeys a second order nonlinear ODE, which passes the Pain-Levé test. And in fact, most of the potentials we found, we were able to write this function in terms of the 6 Pain-Levé transcendence. Just to give you an example, so let's consider a potential with a 4th order integral of motion and a pure quantum one. So it means that the angular part is proportional to H bar squared. Again, we assume separation of variables in polar coordinates. And for this potential, we can indicate explicitly the 4th order and a 4th order integral of motion. The second example I would like to tell you about is this infinite family of superintegrable quantum potentials, but now they are exotic. Again, the radial part is harmonic oscillator, but the angular function, this T of theta, can be written in this form. Let me describe each element. So again, we have a prefactor of H bar squared, and then n minus 2, where n is the order of the integral. We see that if n is equals to 2, this potential disappears as it should be. And the non-trivial dynamics is given by this function W of tau. Tau is the relevant variable, so it's cosine squared of this. So the order of the integral appears in both places as a prefactor, but also in the argument of the angular part. And the function capital W is presented here. So it's given in terms of the most general 6 Pain-Levé transcendent. This 6 Pain-Levé transcendent so satisfies the well-known 2nd order differential equation. This year, some wave functions for this quantum potential, it was shown that they can be expressed in terms of exceptional Jacobi polynomials. This point is important because it's already known that the ASCII scheme can be generated using this superintegrable system, 2nd order superintegrable system. So there is a strong hope that higher order superintegrable system can lead to a similar scheme, but for exceptional polynomials. So this kind of families which are not standard. Unfortunately, in general, for higher order superintegrable systems, so n larger than 2, a complete classification is absent. But when we can start from the very first step, what would be? Well, we can ask if, in the case of separation of variables in Cartesian coordinates, to look and to try to classify any infinite family of higher order superintegrable systems. So this is what the talk is about. And the answer to this question is yes, there exists such an infinite families, and let me describe them. Okay, So integrability, we already have it, because once we impose separation of variables in Cartesian coordinates, in the classical case, this is the Hamiltonian. And then we just quantize the momentum variables and we arrive to the quantum operator. Clearly, this second order operator X commutes or Poisson commutes with the Hamiltonian. So it's an integral of motion for arbitrary functions V1 and V2. V1 depends only on X and V2 only on Y. And the system is trivially integrable. So we can indicate, in addition to the Hamiltonian, another conserved quantity. So now we will focus and we'll try to find another integral, but of higher order, in particular of n order. And the most general n order Hermitian operator, polynomial in momentum, is presented here. The leading part, so the n order terms, it can be shown to have this form. So we can write the leading terms using, well, they are in the enveloping algebra of the Euclidean algebra E2 with basic elements Px, Py, and Lz. Lz is just the z component of angular momentum. And here we have arbitrary constants, this capital A. They are just parameters. And these parentheses, now they denote anti-commutator. Here, of course, we need to say something about these coefficients, which are function of X and Y, this Fj to L. And in order to fix them, we are going to need the commutator with the Hamiltonian. In general, this commutator is a differential operator of order n+1. The generic form is presented here. And since we are looking for another integral of motion, each of these coefficients, which should be 0. So for any value of k and L, this capital Z should be 0. And the coefficients, of course, depends on X and Y, on the coefficients Fj to L here, as well as on the potential. So that's why they are called determining equations. They will fix not only the potential, but also the corresponding integral of motion. If we don't assume anything about the potential, we can write actually those equations. They were presented for the first time by Post and Vintornitz in 2015. And in the classical case, we simply take the limit h bar equals to 0 to get the corresponding equation. So the goal is to find a solution for all these big, huge set of equations. Let me present you some theorem. So a necessary condition for a separable potential in Cartesian coordinates to allow a polynomial integral of order n equal or larger than 2 is that the function v1 satisfies simultaneously two linear ODEs of order n+2 each of them. Explicitly, this is the first linear ODE, and this is the second one. Similar equation can be written for the y part of the potential, so V2, and they have a symmetric form. And they depend on these parameters, this capital A, which before I mentioned it. Using this equation, we can introduce a classification of potentials. They are called doubly exotic and doubly standard. Let me give you here the precise definition. If V1 and V2 are fixed by the linear equation I just presented, we call them doubly standard potential. So we solve these two equations and we have what we call doubly exotic standard potential. Interestingly, if n, so the order of the integral, is larger than 2, we can always find a subset of the parameters in this integral, capital Y, in such a way that all linear equations are satisfied trivially. In particular, the linear compatibility condition from the determining equation are identically 0. In other words, the potential is not fixed by such a linear equation. The conjecture is that if we satisfy trivially these linear equations, then the V1 and V2 will obey nonlinear ODEs. In that case, we call the potentials doubly exotic because they satisfy nonlinear equation. And in this formalism, in this approach, the key element, which is now new, is that in the same way as linear equations appear as compatibility condition, one can derive in a systematic way nonlinear compatibility condition, and they are instrumental to find doubly exotic potentials. Let me emphasize that even at n equals to 3, people knew about nonlinear compatibility conditions, but they were sufficiently difficult to deal with. But then if we take into account the linear equation I just described here, those nonlinear compatibility conditions will contain less parameters than the generic expressions, and they can be solved. So this is the new key element, in addition to linear equations, to write and solve the nonlinear ones. Here, I will focus from hereafter on this doubly exotic potentials. So those equations, those potentials satisfy, by definition, only nonlinear equations. And for any higher order integral of motion, larger than 2, this is the leading term of the integral. It contains 4 times n-1 less parameters, these capital A's, than the generic expression. So it will simplify all the determining equations. Here I present some the lowest examples. Again, let me focus on the leading term. So for an integral of order 3, we only have px to the cube plus py to the cube. For n equals to 5, LC starts to appear in the leading term. So for 3 and 4, it's absent, but for n equals to 5, it already starts to appear. The potentials corresponding to these integrals, if they exist, they obey nonlinear equations only. So this is the main property. And for n equals to 4, since the Hamiltonian and x are trivial integrals, so they are conserved quantities for any potentials, we can easily see that for n equals to 4, no doubly exotic potentials will occur. And this is an artifact of this value of n equals to 4, because for n equals to 6, they will appear. As I said, now the key element is this nonlinear compatibility condition. So let me try to summarize what I mean by this. So we have the generic expression for the n-order integral written here, and also the determining equations that guaranteed that the Hamiltonian and this operator commutes. If L is equals to 0, the set of equations, they will fix the leading term, which I already presented. The next, for L equals to 1, those equations, they tell us these linear ODEs for the potentials, so the standard potentials. And they also define these coefficients fj to L. After that, for L equals to 2, non-linear equation starts to appear for the potential. And this is where we focus on the third level. In a diagrammatic way, this is what's going on. So at L equals to 0, the determining equations, they do not depend on the potential, so we can solve them easily. After that, we go the next level in this well of equation, which corresponds to L equals to 1. They define, of course, the coefficients fj2, and now they depend on the potential. And we calculate the compatibility condition. This is the linear compatibility condition found by Yetarinta, which governs the standard potentials. Here for doubly exotic, what we found is that we can always find a subset of parameters in the integral in such a way that these equations, this linear compatibility condition, is identically 0. So still we can say that the potential is free, but then it will be fixed by the next level of the well of equation. The main difference is that the next level of equation will involve not only the potential, but nonlinear compatibility conditions, equations for the potential. And from this third level is where we find all the generic expression of doubly exotic potentials. We can consider other values of L, for example, 3, 4, and so on. But the main point is that those equations will only constrain the general solution that we find in this third level. So the last part is just some brief summary of the results of these potentials. So again, I consider, I will focus on only two cases, an infinite family of quantum doubly exotic potentials. The first family is characterized by this leading term. So we have px to the n. So n here is written as a 2k plus 1, where k is an integer, and also py to the n. So this is the leading term of the first infinite family of doubly exotic potentials that appears due to this nonlinear compatibility condition. The second family, it's given here. So the leading term contains Lz in power n minus 4. This is the anticommutator with this product of px and py. The second family starts to appear if n is equal or larger than 5. And the first family corresponds only to odd numbers, odd values of n. N is the order of the extra integral of motion. So some examples. For n equals to 3, this is the corresponding integral. So we have px to the cube plus py to the cube. The corresponding superintegrable potential takes the following form. So it's a pure quantum potential because it depends on h bar explicitly. This is the prefactor. And the x and y part are given in terms of the first Pauli transcendent. So this is the equation that satisfies this P1. Again, it's of course separation of variables in Cartesian coordinates. And this result was found by different approach, first by Gravel and Winterlins in 2004, and using one-dimensional algebras, system algebras in one dimension. Gungur, Kuro, Neto, and Nieto re-derived the same potential 3 years ago. Next, for n equals to 5, so we move and we consider an integral of 5th degree with the following form. So the leading term is given, it's again cubic in px and cubic in py. Unfortunately, in this case, we cannot solve the equation, the nonlinear equation for the potential. For example, the x part, v1, must satisfy this fourth order ODE. Here, a0, a2, a1, they are just arbitrary parameters, as well as lambda. And similar equation will occur for the y part. But as I said, unfortunately, we were not able to find the general solution to this equation. The conjecture is that this equation, if h bar is different from 0, it will define a new Pauli transcendent in the sense that the general solution cannot be written using only the 6 Pauli transcendents. So already at n equals to 5, the search of superintegrable system leads us to very interesting equations with this property. So this is one of the, from the mathematical point of view, important that we generate differential equation with the Pauli property. So far, there is no, is not know if it will define a new transcendent, but this is a conjecture. Also for n equals to 5, there is another superintegrable system in which the leading term of the integral is presented here. Unlike the previous case, now we were able to solve the nonlinear equation, so the x and the y part can be written in terms of, in this case, of the fourth Paul-Levé transcendent. So this is the form. Now we can see the presence of this x squared and y squared will help us to have confining potentials and then to study the discrete spectrum. Finally, for the quantum case, let me tell you about this example for n equals to 6. So this is a member of the second family of superintegrable potentials. So the leading term is this anticommutator, LC squared, PY squared, PX squared, and PY squared. The x part of the potential, the x component, takes this expression, so it's given by this expression. We see that it appears P3. So now the third Paul-Levé transcendent enters into the game. And for y is the same, actually, it's symmetric, the form of the potential in y. So the only difference is that here depends on x and here only on y. Again, alpha, delta, and beta, they are nothing but just arbitrary parameters. And they are pure quantum potentials because they are proportional to h bar squared. So before going to conclusions, let me tell you briefly something about the classical doubly exotic potentials. In particular, the case n equals to 5. So this is an element of the second family. So this is the leading term. LC is just the standard classical C component of angular momentum. Px and Py are again the canonical conjugate variables. If we consider such an integral, then the superintegrable potentials, the V1 and V2, they are given by the solution of this equation. For convenience, we introduce this function T1, so T1 prime is nothing but V1, and this T1 obeys this algebraic equation. What's the main difference with the quantum case? So let me go back to the quantum case. The quantum case, the solution, the potential are expressed in terms of Paul-Levé transcendence. So of course they have the Paul-Levé property. But in the classical case, already this property disappears. We conjecture that this is not an artifact of n equals to 5, but a generic property of classical systems, that any doubly exotic potential for arbitrary order of the integral will be determined by equations without the Paul-Levé property. So this is one of the conjectures. And also, since in the classical case computations, everything is simpler, and also the results are very short, let me just briefly discuss the polynomial algebra of the integrals. So using the second order integral of motion, so this one which leads to separation of variables, and the just presented fifth order integral, let's calculate this Poisson bracket to obtain a new trivial integral of motion. Using this capital C, X, and Y, one easily obtain the following algebra. So the Poisson bracket of C with X is proportional to the fifth order integral, and the Poisson bracket between C and Y2, it's nothing but a polynomial expression in X and in H. It means that at least in the classical case, the algebra generated by the integrals of motion, it's polynomial and it's closed. For the quantum case, similar considerations can be done, but I will not talk about them for the time being, and just give you some detailed conclusions what I just said. So in this talk, we consider 2D classical and quantum n-order superintegrable potentials with separation of variables in Cartesian coordinates. So the potential is the V1 but plus V2. The classification of such system is based on the linear compatibility condition this condition was obtained using the commutator between the higher order integral and the Hamiltonian. So this equals to 0. And it's useful because it leads to this classification of doubly exotic, doubly standard, and singly exotic potentials. Doubly standard potentials, they are determined by this linear compatibility condition, so they are solution of this linear equation. But for the doubly exotic potential, this linear ODE is trivially satisfied, so it's 0 without telling us anything about this function V1 and V2. So we need to construct nonlinear compatibility condition. That can be done, and they are very instrumental to determine the generic expression for these doubly exotic potentials. In the quantum case, these equations, the conjecture is that they pass the Pauli-Levé test. I'm sorry I didn't write here, but we check this conjecture up to n equals to 11. So we have a strong evidence that it can be true. And the more important, from the formalisms, the more important point is that it was the systematic construction of this nonlinear compatibility condition. So in this section, let me just summarize the main conjecture of the work that it was done about these new infinite families. Let's consider the first family. So the higher order integral of motion of order n is presented here, and it appears only at odd values of n, so 3, 5, 7, etc. If we take this integral of motion and we solve all the determining equations, the conjecture is that the solution of them will lead to this potential. So it's a pure quantum potential, depends on h bar squared, and it can be written as the sum of the x and y part, and the function capital U obeys a nonlinear ODE of order n-1 presented explicitly here. And with the remarkable property that such an equation will pass the Pauli-Levé test. And as far as in the cases in which we were able to solve the equations, we found they can be written in terms of the known Pauli-Levé transcendents, most of them, but some of them they cannot. So we hope that they will define new Pauli-Levé higher order Pauli-Levé transcendents. This is everything about the first family. So the family which is described by this higher order integral of motion. The second family, it's described with this leading term. So angular momentum appears, and they start to occur for n equal or larger than 5. In this case, the potential also, it's a pure quantum potential. It depends on h bar squared explicitly as a global factor. And now the relevant function, this f, it satisfies a nonlinear ODE, in this case of third order, presented here. So we have the highest derivative in this equation is 3 of the function. Again, the small a's are nothing, sigma and capital gamma, they are just arbitrary constants. And this equation, so this third nonlinear ODE, it was checked that it passed the Pauli-Levé test for the examples we know, up to n equals to 11. But we were not able to find the general solution to this equation. But the test can be done, so we obtain the resonance, everything, but not the solution. So what about the future? Well, of course, there are very clear options. So first is to study in more detail, the polynomial algebra generated by the integrals of motion in generic ways, so for an n-order system, and use this algebra to calculate, let's say, for example, the energy spectrum, the wave functions in the case of bound states, but also, why not, the S matrix, so the dispersion in the case of not bounded solutions. This is closely related to the theory of orthogonal polynomials, standard and exceptional ones. The second point is about the, if any, the search of an underlying hidden algebraic structure of the Hamiltonian. In the TTW potential, this hidden algebraic structure plays a fundamental role in the exact solvability. So we believe that the same approach in this case can lead to important results. Of course, from the mathematical point of view, the question is that if new non-reducible Pauli-Leibler transcendents will appear as we increase n, and what they are. And along the same lines, 3D systems or potentials with a magnetic field. Here, let me finish with some reference on the first, this paper, all the relevant equations, which I didn't present here, the nonlinear equations, you can find them there, and about the separation of variables in polar coordinate, also with Ismet and Lopez Vieira in these two papers we present in detail all the reasons. So let me finish and say again, thank you very much for being here. Thank you.
So thank you very much for an inspiring talk. Other questions?
Can you say something about exact solvability of those new potentials?
Yes, we know only some results, but for the lowest examples for n equals to 4 and 5, some of them lead to these exceptional Hermite polynomials, but in general, we don't know.
But did you find any new exactly solvable potentials or quasi-exactly solvable potentials?
Personally, no, I didn't, but Marquette, Christian Ken, they studied a lot of this kind of potentials, and they have solution in terms of exceptional Hermite polynomials.
Those potentials are non-trivial, or they really provide some type of isospectral deformations of known exactly solvable potentials?
No, it's the same as in the second order. This is isospectral deformation of known potential, yes.
I would, if I may add something, these are highly trivial highly trivial isospectral deformations of either the harmonic oscillator or the anisotropic oscillator with a rational ratio of frequency, or of the 1/r potential. So the energies are given by the algebra. The algebras are known. Yeah, the energies are known. Yeah, they are the same as for the harmonic oscillator. Now and then with one level missing, and that's precisely why it leads to not to the regular orthogonal polynomials or solutions, but to the exceptional ones. Now, solutions that were obtained by Gravel on one hand and Marquette on the other, in the cases n equal to 3 and n equal to 4, the ground state is given in terms of a Pauli-Leibler transcendent, because the potential is already a Pauli-Leibler transcendent. And then they produced raising operators that give complicated relations for the wave functions above the ground state ones. Typically, there's more than one ground state, one basic state, let's say, and there's a tower of states above them. And for those, there are equations that are, of course, non-trivial. So I would say that in that sense, they're exactly solvable. The spectra are obtained algebraically, and the functions, well, there's a lot of information about the eigenfunctions.
So if I may ask, so you're saying that the algebra behind the exceptional, say, Hermite polynomial is known and provided. by this construct?
Yes, yes, it's known up, yes.
What is this algebra?
No, I don't.
Polynomial algebra.
No, it's a cubic polynomial algebra. So let me go back. Sorry for.
The algebra was shown here.
So this is the potential, and then this year was Marquette, Post, and Ritter. For a special value of the gammas in the Painlevé sixth equation, it degenerates into a rational function. So they take this rational solution, substitute in the potential, and solve the Schrodinger equation. And the angular part leads to this exceptional Jacobi polynomials. And it was obtained using a cubic algebra, cubic algebra. So it's known in that case, but of course not the algebra.
Could you give me, the key thing is that you jump some level, right, with exceptional polynomials.
That's right.
Yes, it's
And
absent one of the monomials, yes.
And, but this is, but if you have raising operators, what is the mechanism that at some point you will skip? You will not simply have a ladder of equally spaced states.
You mean that how to generate, how to avoid getting gaps, or vice versa?
Vice versa. How are the gaps? How are the gaps happening?
Exactly.
No, to be honest, I'm not very familiar with this approach of Marquette. This is the how it was done. As far as I remember, they studied in detail this cubic algebra. It's a closed polynomial algebra of the integrals, and then use this. But I cannot answer to that question. I'm sorry, this is not. I don't remember.
Comment that I could make, I can't answer it either. One comment I could make on that is that the orthogonal polynomials appeared in very exceptional cases. And what's exceptional about them is that, as we know, the Painlevé equations by definition are nonlinear and in general. However, we also know that all of the original Painlevé equations, the 6 Painlevé equations discovered by Painlevé and Gambier, have, all except Painlevé 1, have special solutions that are also solutions of linear equations. Yeah, and that is that is where the orthogonal polynomials come in. Now, the exceptional orthogonal polynomials. And the question of why the raising and lowering operators don't give that, don't fill the gaps. Well, frankly, I don't know. That's a very technical question.
No, I don't think it's technical question. It's really a conceptual question. How just with raising or lowering operators you can just really get gaps.
To finish my sentence, I would strongly recommend that either Marquette or Post or somebody else, one of the authors, be invited to give a talk on that.
Okay, this is what I had another question of a different, more general and not. But how do you interpret these what you call the purely quantum potential, potentials with an h bar square in front of them? Do you see them as it's intriguing as arising potentially from some radiative corrections to a certain problem? And have you tried to look at the semi-classical analysis of these problems and what happens then? And why is suddenly when you do the exact computation, you would have higher symmetry? Have you looked into that? What is the meaning of these systems?
No, that's actually a very interesting remark. No, I haven't looked at the semi-classical analysis of this potential, but since it's a global factor, this h bar, at h equals to 0, at 0 order, it is simply free motion. So we cannot take the limit in the solution, but we have to go into the equations because the higher order derivatives, they are proportional to h bar. And that's why the limit in the solution, it's singular. So in that case, we go back to the original equation and then take the limit there. But no, how I interpret it's an open question. Recently, also with Turbiner, we found that for the n-body problem, we can reduce the Hamiltonian, and the price we have to pay to reduce the degrees of freedom of this Hamiltonian and to keep a Schrodinger operator is that we have to introduce, in the quantum case, an effective potential, and this effective potential depends on h bar. That's another way to generate h bar dependent potentials. But if there is a relation with superintegrability, it's still unclear to me. But it's very, I will look into the semi-classical. Yeah, that's very, yeah, thank you.
If I may make another comment on that, just to complement what Adrian was saying. If you take the limit in the actual potentials, you don't, if you take h equal to 0, you certainly don't get the classical case.
Yeah, no.
And the reason for that is that the limit is singular, meaning several of the highest order terms in the equation, let's say we have a fourth or fifth order equation, then typically the coefficient of the fifth derivative at fourth involves h square. Yeah, so the classical equation is of much lower order and completely different and does not have the Penlevet property. Now, to which I would add that doesn't mean there's nothing that one can do with it. Yeah, it's guilty of not passing the Penlevet test, the equation, but that doesn't mean one can't get solutions.
Well, Pavel, I was asking, I understand the mathematical story. Yeah. I was asking more about the physics. What do you claim to describe with such a Hamiltonian? And it's seen there are such potential, but usually they arise as effective potential from a quantum field theory where you compute to a certain perturbation, you add the radiative corrections, and this is where the interpretation comes from. But in non-relativistic quantum mechanics, I'm asking if you had any thoughts. You've encountered this potential for a long time now. Yeah. What is the physical, what do they mean physically?
Well, I guess the answer to that is we have no idea.
Fair enough.
Yeah.
Let me also ask another question. Is it possible to extend this formalism for 3D case for E3?
Yes, certainly it's possible. There's a work done by Snowball already, even including magnetic field for the 3D case. But the idea of nonlinear compatibility condition is not developed in the three-dimensional case. So in principle, it's straightforward, but we have more equations and more determined. So it means that, but conceptually, yes. Technically, I see some problems, some difficulties technically, but at the conceptual level, this approach is very clear. We construct nonlinear compatibility conditions from the commutator between the integrals and the Hamiltonian. This is the key element.
But there's still a complementary approach, and that is through operator algebras in one dimension.
Oh yes, this is.
And then you can glue them together in as many dimensions as you want. That has mainly been done in 2, but there are lots of results. Again, equal you to Marquette on one hand, and to the Spanish guys like Del Olmo, Nieto, Negro, and so on gluing them together in 3 or n dimensions. That is not as systematic as this direct approach. You don't get all of them, but you get a lot of them. And profile only works in Cartesian coordinates.
Adrian, what can you imagine what in three-dimensional case, in the case of three variables, what would occur instead of Pinlevé transcendence?
No, even at d equals to 2, I don't know what kind of Pinlevé transcendence will appear. Even in this classification, as I just mentioned, there are a lot of equations starting from n equals to 3 and 5 that cannot be solved in terms of known Pinlevé. And we asked some expert, Cosgrove, etc., and they cannot tell us about these conjectures, how to solve this equation.
But at least I would not expect I would not expect something to arise instead of Pinlevé transcendence. Yeah, this is very much related to ordinary differential equations and to separation of variables. So once you separate, you're dealing with ordinary
Yes.
differential equations.
Yes.
And it'll be the same Pinlevés. Not necessarily the originally 6, already, as Adrian was emphasizing, already for n equal to 2, you get all 6, by the way, and then when you get to higher degrees of polynomials, you start getting those that cannot be integrated in terms of the 6. With the 6, the question was, can you integrate in terms of known before the Pinlevé transcendence classical
Yeah.
functions? And the answer was no, you can't. Now for the 6, yeah, for the 50 that INS has, for most of them you can. For the 6 you cannot. Now here, I see no reason why when you go to ODEs of order n, you should always get only what you already get at level 2. And indeed, systematic studies in particular by Cosgrove, but also by Biro early and Chazy and other, have shown that other possibilities arise for third order and higher order equations. There's a whole industry of that. Kudryachov is another person. So, any further questions? If not, further comments? Well, if not, thank you very much. Let's thank the speaker and
Thank you.
the seminar.